Today we're going to define and use fractional exponents. So your radical sign is used to indicate roots, and when there's no number right in this location right here, it's considered a square root. So yes, you can have a number there, and it's called the index. It's the small number to the left of the radical symbol, which tells you which root to take. So if I have something right here, the cube root, it's saying, let's do the cube root of 8. You are saying to yourself, what number times itself 3 times gives you 8? Well, 2 times 2 times 2 gives you 8, so the cube root of 8 is 2. The cube root of 27. What number times itself 3 times gives you 27? 3 times 3 times 3 gives you 27, so the cube root of 27 is 3. You can have roots higher than 3. You can have the 4th root of 16. What times itself 4 times gives you 16? That would be 2. So the square root is what we're commonly used to seeing, but you can also have cube roots, 4th roots, 5th roots, 6th roots, and go higher from there. Another way to write a root is by using exponents that are fractions. The index here is 2. The square root of 4 can also be written as 4 to the 1/2. They both mean the answer is 2. So the square root of 4 is 2, and 4 to the 1/2 means you're taking the square root of 4, which is 2. So let's look at this. If you have a to the 1/2 power, that means you're taking the square root of a. If you have a to the 1/3 power, you're taking the cube root of a. If you have a to the 1/4 power, you're finding the 4th root of a. Let's look at this with numbers. "25 to the 1/2 power is really asking you to find the square root of 25, which is 5. 27 to the 1/3 power is asking you to find the cube root of 27, which we already talked about is 3. And 16 to the 1/4 power is asking you to get the 4th root of 16, which is 2. You can have a number raised to a fraction such as 2/3. When you do that, the index, the denominator is your index right here. And then your numerator is your power right here. So you're finding the cube root, get that answer, and then you square it. A to the 3/4 power, you're finding the 4th root of a, and then you cube the answer. Here it's the 5th root of a, and then you square the answer. Let's look at it with numbers. 27 to the 2/3 power is saying the cube root of 27 squared. The cube root of 27 is 3. 3 squared is 9. The 4th root of 16 is 2, but then you have to cube it to get 8. The 5th root of 32 is 2. 2 squared is 4. If you have 25 to the negative 1/2 power, now we've got the fractional exponent and we've got the negative exponent. I look at this and I say, okay, the negative exponent is going to flip it to the denominator, and the 1/2 power is telling me to take the square root of 25. So my answer is 1/5. Try number 4. See what you can come up with. Try 5 and 6. Number 7. The approximate number of calories C that an animal needs each day is given by C equals 72 m to the 3/4 power, where m is the animal's mass in kilograms. Find the number of calories that a 16-kilogram dog needs each day. Well, let's go through this. So C equals 72 m to the 3/4 power. Let's substitute what we know. M is mass, the mass is 16. It's 72 times 16 to the 3/4 power. It's 72 times the 4th root of 16 cubed. The 4th root of 16 is 2 cubed. So it's going to be 72 times 8. That gives you 16,576 calories. You can try number 8. Let's go back to variables, since we haven't talked about variables with an index higher than 2. If you remember, when we did the square root of x to the 4th, since it was the square root, we just divided by 2, and we got x squared. Or if we did the square root of x to the 10th, again, we divided by 2, and we got x to the 5th. Well, if you want something like the 3rd root of x cubed, you're going to be dividing by 3, so that equals x. If you want the 3rd root of x to the 15th, that's going to be x to the 5th. So up here, the 4th root of a to the 4th, 4 divided by 4 gives you just 1, so it's a. b to the 20th, the 4th root of that, 20 divided by 4 is 5, so it's b to the 5th. Go ahead and try number 10, 11, and 12. And that's it. So bring that to class and we'll go over it.